All right. Okay. So hello, everyone. Welcome to the first seminar for Geotopics Seminar for this semester. We're still going to do Geotopics online for this semester due to COVID. And today we open with Dr. Petr Brož. Petr is a geomorphologist, and his area of expertise in particular is volcanism across the solar system. Petr obtained his Ph.D. in 2015 at the Faculty of Science of the Charles University in Prague. And during this study, completed also an internship at the German Aerospace Center and at the Open University in the UK. Among the prizes that he won the Otto Wichterle Award of the Czech Academy of Science for Young Promising Scientists. And he was also awarded a prize in 2016 for a new and inspirative outreach model of plate tectonics. Petr is also really dedicated to public speaking and writing in the attempt of popularizing geosciences in the context of exploration of the solar system. And he now works as a researcher at the Department of Geodynamics in the Institute of Geophysics of the Czech Academy of Science. Today, Petr will be talking about sedimentary volcanism on Mars. So without further ado, everybody welcome Dr. Petr Brož.
Okay, thank you. Thank you very much for a nice introduction. It's my pleasure to be with you and to show you some results of our work. Today, I would like to speak with you about the sedimentary volcanism on Mars. And let's say that the presentation would be composed of two parts. The first would be to give you some general overview about the sedimentary volcanism on Mars, to show you some evidences or some areas where we believed sedimentary volcanoes are situated. And the second part would be about experiments. And I will show you later or explain a bit later which type of experiments we performed and what was the motivation. As you can see, this work was quite a cooperation with a bunch of other peoples. I would like to name them. It was Ondřej Kryza, Lionel Wilson, Susan Conway, Ernst Hauber, Adriano Mazzini, Jan Rák, Manish Patel, Matt Balm, Matt Sylvest, and Niels Miller. And I have to say that without the help of them, our experiments would never bring such interesting results. So, okay. First of all, let's say a few words about Mars. I'm sure that all of you know that Mars is a terrestrial planet. It means that it has a hard, rocky surface. It's roughly the half size of the Earth. And because it's smaller, it's lighter. And because it's lighter, it has a lower gravity. The gravity is roughly 1/3 of the gravity of the Earth. And this is one aspect which is quite important. Why? Because many geological processes can be affected by gravitation, including the sedimentary volcanism. The second important part, which is good to know about Mars, is that Mars has an atmosphere. However, because Mars has a lower gravity than Earth and Mars has no magnetic field, the atmosphere is much weaker than the atmosphere of the Earth, and roughly the atmospheric pressure is around 7 millibars, but it really depends on the place where you are measuring the pressure on the surface of Mars. Why? Because you can measure the pressure inside the Hellas Basin, which is the really large impact structure on southern hemisphere, and the pressure would be there high enough to allow the presence of liquid water for a short period of time. Or you can measure the atmospheric pressure on the top of Olympus Mons, and you would be measuring almost a vacuum. So you really have a large variation in pressure in different parts of Mars. But it would be great if you will remember that in general or in average, the atmospheric pressure of Mars is 7 millibars. So that means it's roughly 170 times weaker than the atmosphere of the Earth. Okay, this is now the surface of Mars. For those of you who are not familiar with this image, this is a topographic map. The different colors are showing different heights, and you can see that Mars has two very different hemispheres. while the southern hemisphere is full of impact craters and is standing much higher than the northern hemisphere, it's saying you that the southern hemisphere has to be older and that the northern hemisphere has to be younger. However, what is important for us today is that in this part, I hope that you can see the cursor of the mouse. In this part, we have some really high mountains. And today we know that these mountains are actually volcanoes, and this entire part of Mars is a Tarsis, it's a huge volcanic province. So we have really nice evidences that Mars was volcanically active in the past. However, we also have these huge flow-like features which are named as outflow channels, and we believed that these features were formed by the movement of some liquid, and today there is almost consensus that the liquid which was flowing here was a liquid water. So it means that there was also a water in the history of Mars, and this is important because now when you are searching or studying the surface of Mars, you have to consider all the time both mechanisms, water-related and magma or lava-related mechanisms. And this is especially the case for kilometer-sized features, which you can find on Mars. And these are the edifices which are in my heart, because I spent with them almost like 10 years by studying them. And you can see that these features, they are representing really diverse group. You can see that we have some really nice looking conical landforms. In other places, we have much more like pancake-like features. Sometimes we have some domical structures, or we can have just flows. Some of these features are related with the flows, some others are superposed on them, and so on and so on. Some are clustered, some are standing alone. And I don't really want to spend here so much time, but I would just say that there is a problem, because if you will go into the literature, you will find that there is, let's call it, ongoing debate within the scientific community whether these features, these small conical structures, whether these are the results of matte volcanism or igneous volcanism. It's quite tough to decide. Why? Because when we will have a look about the results of small-scale igneous volcanic eruptions, we will discover that they show incredibly large variation in their shapes, sizes, and also in the mechanism of their formation, because there can be formed by effusions or by explosions or something in the middle. And these variations are causing that you can have really domical features, you can have conical features, you can have some ring-like features, some table mountains, and so on. So there is really huge variety in their shapes. What is really important here, that you can find such features almost everywhere on this planet. They are situated in all possible tectonic regimes, so they are not really rare. However, when you compare this with matte volcanoes, you can find that the matte volcanoes on Earth, they are also showing wide variations in their shapes, sizes, mechanism of their formation, but there is the huge difference. And the difference is that sedimentary volcanoes or matte volcanoes, they are generally located in really specific areas when some important requirements are met. So you cannot really find them everywhere. There is a question, how to distinguish between these two groups? On Earth, this is really easy. Why? Because you will ask your friend, take a hammer and take a sample from the flow. And if the hammer is in fire after a few seconds, you know that you are playing with lava and not with a mud. However, this is not the case for Mars. Why? Because we don't have a geologist there yet, and because there are no active flows which we can observe and which would help us to to find out what the features which we are observing, what they are. So we have to work with something else. We are mainly working with the morphology, morphometry. We are trying to understand the geological context of the features. We are working with the spectra, and we are working with the modeling. And the modeling, I mean both numerical and analog modeling. However, there are some huge problems with this approach. Why? I would like to show you this on this satellite image. Is a CTX mosaic. It means that the resolution per pixel is 5 meters, and you can really see the surface of Mars in nice detail. And over here, you can see we have some cluster of some conical features, which are surrounded by some flow-like material. Most of them are breached. The height of the floor is quite often situated below the surrounding planes. So it means there was some active process of deepening of the floor. And yeah, and in principle, if you will try to find what these features are, you will end up with two papers. One is by Jim Skinner and Kenneth Tanaka from 2007. And in this paper, the authors are saying that these features are Martian equivalents to terrestrial sedimentary volcanoes because there are bearing morphological and morphometrical similarities with their terrestrial analogs. However, there is a paper by me and Zauber in which we are saying, no, these features are hydrovolcanic tuff rings and tuff cones. Why? Because there are sharing morphological and morphometrical similarities with the tuff rings and tuff cones. So now is the question, who is right? Honestly, I have no idea. Both papers are showing some interesting arguments, but none of these papers can give you a real answer. So we are unsure what these features actually are. Again, if you will jump to other place, these are some cones which are situated inside the Coprates Chasma. This is part of the huge canyon system Valles Marineris, which is on the surface of Mars. And again, you can see we have a nice conical looking features which are associated with some flow-like units on which they are superposed. And there's a paper by Chris Okubo from 2016 in which he's giving a really good argument why he thinks that these features are sedimentary volcanoes. However, again, there is a paper by me and several other people in which we are saying, no, these are not sedimentary volcanoes, but these are scoria cones or maybe tuff cones. Why? Because their shapes are in the agreement with such conclusion. We discovered some minerals which are also quite often associated with the volcanic activity and because of the geological context. Does it mean that we are right? Again, I don't know. Both papers are giving a good arguments and we cannot be sure. Finally, there is a place on Mars which is named Chryse Planitia, and in this particular place you can find something around 1,200 such a pancake-like features, such domical features, and some really weird stuff. There are some details. You can see that there are some nice-looking cones, such a pie-like features or pancake-like features. There are some domes. There are some chaotic, bright terrains, and finally, there are some huge kilometer-scaled flow-like features, which Goro Komatsu, with a bunch of other people in 2016, described as the result of sedimentary mobilization or sediment mobilization. And then there is a paper by me and Zauber and 3 other people, which would probably a bit surprise you, because in this case, we really tried hard to disprove that these are sedimentary volcanoes, but we failed. We have to admit that we have to agree with the Goro Komatsu statement that these features are most likely Martian analogs to terrestrial mud volcanoes. Why? because we tried to study their spatial distribution, and we discovered that these features are associated only with the sedimentary plains. You cannot find them on a slightly elevated places, which are representing the older crust, which is not formed by sediment. So this would be unlikely. Such distribution would be really unlikely for igneous volcanoes, but it's quite common for. Oh, sorry, it's necessary for sedimentary volcanoes. Why I'm showing this? Because when I was studying this area, and I really was trying to disprove the existence of sedimentary volcanoes on Mars really hard, I actually asked a simple question. Okay, if I will start to believe that my results are leading me to the conclusion that these are sedimentary volcanoes, I would like to know answer for the question whether the liquid mud can actually propagate on the surface of Mars. Why? Because I know that water is unstable on Mars. This is a phase diagram which is showing you the stability of water in the dependency of the temperature and the pressure. And in this part, marked with the red, what's this? Sorry, I will say ellipse. I know it's not ellipse, but I don't know how to say it in English. Sorry for that. So with this red feature, you can see that there are theoretically some places where the water can be stable on Mars, but mainly it's not. So I was like, that's strange, because if I would like to have a sedimentary volcanoes on Mars, that means that mud, which is a mixture of clay and water with some ratio, would be able to move there. But this was suspicious for me. So I really tried to find the answer for this easy question. And what I end up was that I discovered only one paper by Lionel Wilson and Peter Mognis-Mark from 2014, in which such aspect was partly touched. And I actually realized that we don't really know the answer for such important question. So what I did was that I asked for funding. I asked Europlanet 2020 if I can use one facility, namely the large low pressure chamber at the Open University. And I was lucky because I got the money from them. I would just like to say to all of you, if you can apply for this travel money, go ahead, because you have to write only 3-page long proposal. It's only about the science. You don't have to care about the funding, anything. It's really easy, and you can get access to really cool laboratories or some other interesting places on this planet. But anyway, so we get access to the chamber. As you can see, the chamber is actually quite large. It's roughly 1 meter to 2 meters in size, meaning that I can fit inside the chamber. If Andrzej Kriza, that's the guy on the movie, would close the chamber, I would be trapped there inside, and he can just depressurize, and I would not really enjoy my day. But yeah, and I would like to say that the head of the lab is Dr. Manish Petle, and I'm really thankful to him that he allowed us to play with the mud inside the chamber, because as you will see, it was a bit crazy. Okay, important question. I'm sure that this is something what you would ask me in the end. Which medium did we use? We used a clay from the claystone rock clay, which is situated in the Czech Republic. It was a bentonite, and it was created by the alteration of the volcanic pyroclastic material. Now, important question, is this a good analog for Martian clays? Honestly, we have no idea. Why? Because we don't really know which type of clays are on the surface of Mars. This was the first generation of experiments, so we have to start with something, and we were like, okay, let's go, let's try to use this type of the clay, because we know that this is a material which was formed by alteration of pyroclastic material. That's something what we are aware that such material is present on the surface of Mars. Okay, we were also thinking about the viscosity, how viscous our mud should be, and we decided that we would like to play with the viscosity of mud, which is quite close to viscosity of the water, I would say, meaning that the mud was moving really fast when we released over the surface. If you would like to duplicate our experiments, there is important note. Salinity plays a critical role. If you would not add a bit of salt in the water, there will be no suspension of the clay particles within the water, and that would ruin up your experiment. So you have to make water a bit salty. Okay, this is the experimental setup. As you can see, it's quite simple. As I said, this was the first generation, so we decided to make to make it as simple as possible. In principle, we had a trail which was infilled by roughly 5 or 10 centimeters, something between 5 to 10 centimeters of sand. The sand and the trail was pre-cooled to the temperature of minus 20 degrees of Celsius. There were a bunch of thermocouples, so we were able to measure the temperature of the sand or of the material which was then released. There was several cameras which were recording the experiment, and there was a reservoir for the mud. The reservoir, sorry, I would say a container. That's easier word for me. The container was hanging above the surface. That's something which we are aware that this is not the situation for Earth, because normally the mud would came from below, from the subsurface. But this was the easiest possible setup which was possible to produce. So yeah, we know that the place where the mud was released is not really saying the truth about the behavior of the mud. So we just focused about, let's say, about the downer part of the flow. As you will see now, to do something inside the chamber is not as easy as you may think. Why? Because when you are working inside a low pressure chamber, you cannot put your hands inside the chamber once it's closed. So that means that the experiment, you cannot fix the experiment during the run of the experiment. So we had many, I don't know how much time we have, but many failures, really a huge amount of them. But after a while, we learned it, or we mastered our experimental setup, and we were able finally make some experiments. This would be 2 movies to show you how the experimental mud would be behaving under the normal atmospheric pressure. So it means that the chamber was opened. The temperature of the sand would be minus 20 degrees. The inclination of the table is 5 degrees, and we are releasing 500 milliliters of mud over 2 centimeters thick layer of sand. And this would be really boring for you, I'm sure, because this is showing what you are expecting from Earth. I'm showing this to you only as a reference, so you know how the mud would be behaving under the normal terrestrial circumstances. You see that the flow is moving downhill because of the gravity. You see it's spreading laterally, and part of the water is infiltrating into the sand. There is no real freezing, and yeah, it's moving as water over the surface. Once the experiment ended up, we excavated, or we removed the sand, and we observed the infiltration of the water. We can see that the clay was not able to infiltrate down into the sand. So yeah, that's really something obvious. Okay, now let's do the same experiment. Everything is absolutely same. The only difference is the atmospheric pressure. Does somebody of you want to guess what would happen? No? Oh.
Would it freeze?
Yes.
Swifter?
Yes, but how freeze? What do you expect?
Like it would move a lot slower.
Sorry, one more time, sorry?
It would drip a lot slower, like it wouldn't be as smooth as on Earth.
No, not really. Pavel, thank you.
Would the water evaporate, like bubble?
Yeah, partly as well. But now you can see it. Because actually there is a boiling. So there's an evaporation of the water and there is a boiling. But the boiling and the evaporate cooling is causing that the flow is starting to freeze. But it's not freezing as the entire flow, it's freezing only on the surface. So we were observing the formation of icy crust and the mud was moving by such weird way. And once the experiment was over, we repressurized the chamber, we excavated the flow, and we discovered that the mud is still liquid inside. It looks like a delicious chocolate biscuit, but it's just really super cooled mud, which was surrounded by icy, muddy crust. When we studied this crust, we discovered that quite often it's full of variously sized bubbles, which are evidence of intense boiling during the course of the flow. And that means, that was showing that the formation of the crust was actually able to protect the mud from freezing. Why? Because once the crust formed, the evaporate cooling, which was removing the heat from the mixture, actually had to stop because there was no low atmospheric pressure around the liquid mud. I'm not sure. I'm sorry. I'm not really sure if I'm now explaining this clearly enough in English, but I hope that I will be able to explain this aspect.
Peter, I think you say it sort of encases itself, and therefore the pressure is raised, so it doesn't boil. Is that it? Yeah, exactly. Exactly. That was what I was trying to say. That because of the icy crust formed, it protected from the atmosphere. The boiling stopped, the evaporate cooling stopped, and the mixture was really protected from the harsh environment. Thank you. This is just the figure which is showing you the results of our experiments. This is 3 experiments under the normal pressure. This is under the 7 millibars, but with a high release rate, and this is 7 millibar pressure with a low release rate. What is important here are actually the topography, because you can see that when we release the mud under the normal pressure, that the thickness of the flow was, let's say, few millimeters. I mean, like 1 or 2 millimeters. However, when we released the mud under the reduced atmospheric pressure, the thickness was several centimeters. And I hope that you know where this is going. If you are lucky enough, or if you were lucky enough and you visited Hawaii, and you observe some Pauehoe lava flows, they are actually propagating by this way. Why? Because as the lava is moving over the surface, it's cooling down, it's making a crust. There is a new batch of lava which is inflating the flow, and you are increasing the thickness of the lava flow. And in our experiments, we actually observed exactly the same behavior, however, in our case with the mud. And this is quite interesting finding. Why? Because we had a tendency to interpret features on the surface of Mars as a lava flows because we discovered inflation of the flow. But we are showing now that this is not the case, because even the mud on Mars can inflate because of the formation of the icy muddy crust. So this is making interpretation of the superficial of the features on the surface of Mars a bit complicated task. if you have only a satellite data. I know what you would like to say now, because I heard this question like many times before. What about the scaling? Because what we just made was an experiment which was a few centimeters in thickness, and the length was a few dozens of centimeters. So we were like, the scaling would be the issue. So let's make an experiment. And what we did was that we made a muddy puddle, which it was a small crater. We infilled it with 1.6 liters of mud, and we just observed what would happen. As you can see, there was a huge amount of boiling. The boiling was causing a huge amount of small-scale explosions, so the mud was flying everywhere. And when the technician who was behind this chamber, he was helping us with the experiment, saw this experiment, he was like, oh, Jesus Christ. He would not be able to repeat this experiment because we are afraid he would destroy with the next round the chamber. So this is the only experiment which we never triplicated, but it was still worthy for us to observe what would happen. Because when I will show you the entire movie, which is now speed up by 50 times, so the original footage was 33 minutes, you can see we have a huge amount of boiling. Then there is some time when the boiling is gone, and there is some, it's a bit silent. But here we go again. We have ice. So even if you would have a flow with much higher thickness, which would be up to, in our case, it was around 10 centimeters, we would end up with the formation of the icy crust. Again, when we finished this experiment, we opened the chamber. We discovered that the mud is liquid under the protection of the icy crust. Then we wanted to know how deep the boiling and the evaporate cooling would be taking effect. So we took two pipes, transparent pipes, and we infilled them with two different viscosities of mud, and we just observe what would happen. Now that the movie is speed up by the factor of 15, and I hope that you can see it, but we have bubbles even here down below. This is like 50 centimeters. So you can see that the boiling and the evaporate cooling is actually occurring to the depth of a few dozens of centimeters. We also measured the drop of the temperature. We actually discovered that the temperature is quite stable in the downer part, and the active cooling of the mud is just occurring in the upper part, which was quite interesting observation, because it's saying you that under the, let's say, 20-30 centimeters, you can have a mud with a quite warm temperature, which would be nice potentially because of the astrobiology, because of some the life can potentially live there. Habitability, I think, is the English word. Sorry for that. It's nightmare. Okay, so we end up with this new conceptual model in which we are saying, okay, if we would have mud extrusion on the surface of Mars, I mean, like now when the pressure is 7 millibars, what would happen is that you would have a liquid mud which would be moving from the vent. Because of the boiling and evaporate cooling, you would have a formation of icy crystals. They will be merging together, and after a while you would have a formation of icy blocks which would be floating. They will be merging, and they will build a crust. Once the crust is there, the boiling would stop, the evaporate cooling would stop, the mud would be propagating under the protection of the crust to the edge of the flow. The mud would be building pressure. It would be forcing to the crust, and this would cause that the crust would break. Once the crust would break, the mud would be exposed to the environment. The evaporate cooling and boiling would start, and the process would repeat as long as you have input of the magma. If you would like to know more details, there is a paper which was published last year in the Nature Geoscience from me and my co-authors. Everything is described there. You can even download the data, the movies, and so on, so you can have much deeper look if you would be interested. What we believe that we can explain with this model, we are still aware that this was just the first swallow. We cannot really say that we are able to explain everything. We believe that now we understand how the low viscosity mud would behave. Maybe we can explain with this mechanism even a medium viscosity mud flows, but definitely we are not able to explain with this mechanism highly viscosity mud flows, which are also quite common on Earth, or we cannot really explain a kilometer-sized flows because we were playing with the small volumes. However, and I'm not sure if this would run. Sorry, I will just. I hope you can see the movie now. I just want to show you this because normally huge floods, they are not propagating as, you know, like a couple meters high wave, but they are quite frequently propagating by decimeters or centimeters thick flows, which are slowly increasing its height. And I personally believe that our experiments can partly explain the behavior of these huge flows on their edges, because these edges would be really affected by the boiling and evaporate cooling. So this is a really nice terrestrial analog where our experiments can actually play some role. Okay, I will just jump. When we finished these experiments, we were like, but you know that Mars can be a bit warm. What does it mean? Because we, based on the data from the satellites orbiting Mars, we know that sometimes there can be temperatures on the surface which would be above the freezing point of the water, above the 0 degrees of Celsius. So we were like, okay, let's try to make an experiment just for fun to see if the temperature of the surface is important for the freezing of the mud flow. So this is just to show you again as a reference the experiment, the results of one experiment which was performed under the normal atmospheric pressure. Everything is same as previously. The only difference that the temperature of the sand was the room temperature, so roughly 20 degrees, plus 20 degrees of Celsius. Yeah, again, you can see that nothing really changed. This is, again, quite boring stuff. Now, let's change the atmospheric pressure. Do you want to guess what would happen again? Somebody?
It's going to boil more vigorously, I'm guessing.
Yes, you are 100% right. Do you want to guess how violently?
Well, I think violently enough that they're not going to let you do the experiment twice.
Actually, we were lucky enough because as you will see, now the mud is behaving quite differently. The temperature of the mud is causing crazy boiling, but the mud is still able to propagate. And have a look how it is propagating. It's not flowing, it's flying. Because of the boiling, each bubble, I mean, the mud is boiling. So it means that the bubbles are causing that the edge of the flow is jumping or vibrating like this. And now remember my second slide, what I said about Mars. Mars has much lower gravity than the Earth. The gravity is roughly 35.
It's like surfing. It's surfing, Peter. It's surfing.
Surfing. Yeah, I think it's actually levitating. It's like a levitation. So if you are lucky enough, and you would be standing on the surface of Mars, and there is a mud eruption close to you, and the temperature of the surface is, let's say, 10 degrees of Celsius, there will be a small droplets of mud flying around you, really like above the surface. And I think this is quite crazy because this is the type of the behavior which we are not which we are not familiar from Earth. So it's somehow hard to think about it when you are doing your numerical models, because this is something which is a bit out of our imagination for a while. I mean, once you will see it, it's so obvious, it's so clear. The physics behind it is actually quite simple, but before you will see it, it's like it's really hard to say. This is just a few images which are showing really that the flow is levitating, or if you would like to say hovering. There is also second part of the image, sorry, of the figure, which is showing you that there was some small boiling causing ejection of the sandy particles around. So there was a rim formation, and there was also a formation of the crust because the sandy grains were merging together with the clay, and there were building a sort of crust again. And as in previous case, once there was a crust, the mud was protected from the environment, so there was no boiling and the mud has to be released again. This is just to show you the resulting morphologies from above. You can see that we end up with a totally different morphologies than in experiments performed under the normal pressure. So this is something quite interesting. We are not definitely saying that we should look for such morphologies on the surface of Mars in the case of kilometer scale flows. We are not as crazy that we would like to compare these centimeters sized experiments with the kilometer-sized flows, but we are saying that you should probably expect different morphologies. We don't really know how different, but as you can see, the mud would be moving in really strange way. We also discovered that the mud was actually able to self-bury. It was able to propagate deeper because the boiling was causing the ejection of the grains from the place where the mud was propagating. So it was self-burying. I hope I can say this. So we wanted to know how deep the mud can actually dig itself into the sand. So we took such a plastic box, the height was like 30 centimeters, and we ran the experiment again, and we discovered that there is some type of threshold, or some better to say some depth to which the mud can self-bury it, and once this depth is achieved, the sand grains cannot be ejected away, so the mud would be flowing as you would expect. So there were no more explosions and ejections. The depth was something like 5 to 6 centimeters. Again, now there is a paper about this behavior. It's we presented a new conceptual model of the mud movement over the hot surface in the low pressure environment. And we are saying in this paper that there will be a huge boiling. The boiling would causing the hovering or levitation of the mud flow. Once the gases are gone, the mud can actually touch the surface. It would be sliding for a while, and after that, it would form, let's say, a channel or some sort of a valley which is surrounded by a clay. The mud can move through this channel, but once it's over, it will split from the channel. It would touch the sand again, and the entire process would repeat as long as we have a new input of the mud. If you would like to know more details, please again read the paper from last year. It was published in Earth and Planetary Science Letters, and I also wanted to know that, I also wanted to say that once we observed this behavior associated with the levitation and with the boiling, we actually realized that in reality, probably the processes on Mars would be working both in this case of the same mud flow. Why? Because important is that the boiling and evaporate cooling is removing the heat from the mud, but also from the surface over which the mud is propagating. So even if you have a warm surface at the beginning, the evaporate cooling and boiling would remove enough heat that there will be a transition from the warm surface into the cold surface. So you would have a transition from boiling into the freezing. So there should be actually both mechanisms operating during the course of one mud eruption. What else? And we are going into the end. Is this the end of the story? Definitely no, because there are so many unknown parameters. For example, I would like to show you the experiment in which we played with a bit highly viscosity mud, and you can see something different. You can see that the mud is actually increasing its volume. Again, that's something obvious now. Once I will say this to you, you will be like, oh, that's right. Because of the higher viscosity, the bubbles cannot run away from the mud. Once you have an icy crust, there are still some small fractures, so the bubbles are still increasing its volumes because they are somehow in connection with the atmosphere, causing that the entire structure it's increasing its volume. This is something what we believe was operating on the moon. It's called as volcanic foams, and this mechanism probably would also operate in the case of sedimentary volcanism. And now think about it. We are believing that a sedimentary volcanism is not operating only on Mars, but also on Ceres, the dwarf planet, where you have almost vacuum. And because you have a much lower atmospheric pressure, the bubbles would have a tendency to increase even more. So probably we should expect some mud foams to be present on the surface of Ceres. So this is just to show you, that there are some other parameters which can totally change, or sorry, not totally, but quite significantly change the way the mud would behave if you change some parameters. Is this the end? No, because the salinity would play a role. We would like to know how more more salts would change the way how the mud would propagate. The slopes would play a role, volumes, eruption rates, geometries of the conduits, and many more different parameters. Actually, I should be in England now to making more experiments, but because of the COVID, the trip was postponed. But we are planning to touch some of these questions in upcoming months once the university is open. But in principle, you can really, if you have an option to play with the low pressure chamber, go ahead, because you will discover that there is so much unknown parameters which have to be explored before we will understand how sedimentary volcanism would actually operate on other bodies across the solar system. Okay, take-home messages. First of all, I would like to highlight here that it's incredibly hard to distinguish between igneous and sedimentary volcanoes on Mars and on other bodies across the solar system, because especially on Mars, both are theoretically possible, and there are sharing many similarities in morphologies, morphometries, sometimes even in the composition. They can be in they can be in the same geological context and so on. So if you would be doing a study in which you would be trying to distinguish between these two, please take your time, think about all possibilities, because you can easily discover many papers which are saying these are igneous volcanoes or mud volcanoes on Mars because they look like one feature in Idaho or somewhere. So this is not the best way how to make a science. So please really try to think about it. A comprehensive approach, yeah, that's right, that's what I just said it. And there is one more thing. Interestingly enough, there is no good numerical model which would be able to predict or explain the formation of sedimentary volcanism on Mars. So if you are a skilled coder and you would like to spend, let's say, 5 to 10 years to playing with the code, this is a nice opportunity. And probably the most important take-home message which I would like to highlight for you, and I have to say I made this picture only for you, try to think outside the box. I hope that I just show you that it's not the best way to say that these features on the surface of Mars are mud volcanoes because they look like a mud volcanoes on Earth. My talk was trying to show you that you have to understand the physics first behind the emplacement of the material before you would like to make such conclusion. And to think outside of the box, it's actually quite hard because you really have to, be sure how the different environment would change the way the material which we are so familiar with it from Earth would behave. And this is not just the case for Mars, but even if you would be working on the bottom of the ocean, because of the high pressure, the material which would come to the bottom to the ocean floor would be behaving differently than the material which came to the surface on land. So really, I think this is the hardest part of the science. Try to keep your mind open and every time think about all the consequences, how the environment would affect the process which are you trying to investigate. And that's it from my side. Thank you very much for your attention. And if you have any questions, I'm happy to answer them.
Well, it was a fantastic talk, Peter. Could I lead with the first question?
Yeah, go ahead.
I mean, I really enjoyed it. The question is, and it might seem naive, is that I do know that from looking at planets in our solar system, that there's many other, well, elements or sometimes compounds which act in liquid form, which are not liquid water. You hear about methane lakes, for example, on some, other planets. Is there anything else which can act like liquid water on Mars under that very low pressure and often low temperature?
Yep.
If so, what is it?
Yeah, there was actually, especially in the 70s and 80s, there was a debate whether these large outflow channels cannot be formed by the liquid CO2.
Yeah.
But the problem is that, the problem. It's not the problem, that's the science. Today we know that everywhere on the surface of Mars where you will look, you have ice. It's beneath the surface. I mean, not really everywhere, but on many places. The polar caps are formed by this. And, the easiest explanation is liquid water. Why? Because to produce a huge deposits of CO2 ice below the surface, which would be, capable to come to the surface, this would be incredibly hard. So the easiest explanation is, okay, because we have a water ice everywhere, there should be some aquifers, because we know there is a huge cryosphere, and that's the way. You are right that, for example, if we would study the Titan, the moon of Saturn, this is exactly the place where no, sorry, not hydrogen, hydrocarbons.
Methane. I think it's methane and hydrocarbons.
And methane, that they are present. So you would have to change the liquid which is there. But for Mars, really you have two liquids, and that's the lava and the water. For example, on the moon, you can rule out the water because there were never conditions to allow a liquid water to be present on the surface. So if you have there the huge, how is it in English? The huge valleys, which look like dry rivers.
I think they called them canals. The early observations.
I think it's valleys. There's Sinus riles. That's the word. Sinus riles. They look exactly like dry rivers on the surface of the moon, but they were formed by the movement of incredibly hot lava, which was able to thermally erode the surface over which it moves. So this is, sorry, just to make a shortly, it really depends on the context, on the body. And in the case of Mars, the CO2 theory, it's quite unlikely because it's quite complicated.
Yeah, very good.
Sorry, it was too long.
I have a question.
Yep.
That was a great talk, very good. And so I was thinking that, of course, we don't have any verified samples from Mars, unless you believe the SMC meteorites, of course. And so during these processes that you're talking about, it strikes me that there would be tremendous opportunities for chemical changes, not only in the precipitation of cements and carbonates or sulfates, but also in the fractionation of isotopes of various different elements, which then get precipitated in these minerals. And so, although we don't have the samples, it strikes me that you could actually incorporate this into your experiments by seeing what was actually precipitated, or if there are any chemical changes during your sort of vacuum experiments, by using fluids which had high salt contents, for example, and when they evaporate in the low vacuum, that would precipitate carbonates, and then that process itself would cause different chemical changes in the, say, the stable isotopes of oxygen. And then you could predict that. You could predict it, model it, measure it, and then once we do get samples from Mars, in return samples, you could actually test this idea.
Thank you. That's interesting idea. I never actually, I was never thinking about such possibility. Thank you.
So can I ask a question quickly? Thank you, Peter. This was a very, very interesting talk. Very, very nice presentation. Appreciate it.
Thank you.
You may have mentioned it, or I may have missed. Would the difference in gravity impact the particle behavior or the physics of particles? Or if so, it should be fairly, I suppose, straightforward to model, or not? You would see surprises that then in hindsight would say that's actually how it should happen.
Yeah, so in principle, I don't believe, or I don't think that the gravity would change the way that the mud is freezing, because the freezing is not associated with the gravity, it's associated only with the removal of the heat. In the case of the levitation, yes, the gravity would change the way because the mud can jump higher. And then there is important consequences associated with the gravity, because the feeding dikes would be wider, they would be longer, the aquifer body has to be deeper, and so on and so on. So there will be many variations. But for our experiments, I don't believe that this is important, because we were really trying only to describe the new transport mechanisms of the mud movement over the surface, freezing and the levitation. And this is, quite straightforward. But if I would like to model the entire formation of the sedimentary volcano, the gravity would be super important, because we know that for example, we know that because of the friction between the particles, the flows should be longer on Mars than on Earth, and so on and so on and so on. So it would be a really complex process, but still these two basic principles would be operating on all other bodies. So. Somebody else? Yeah.
I have a question.
Yep.
If you had a choice of what samples or what information to collect from a potential mud flow on Mars, what do you think you would prioritize?
Personally, I would go into the Christ Planitia to bring some samples of these mud flows. And why? Because they are giving us the opportunity to study the material from the depth of a few hundred meters or maybe even a few kilometers. And these areas obviously has to be full of water, and there has to be some heat because the water was liquid. And this is quite interesting because, as I said before, this may be a paradise for Martian microbes if there ever existed on Mars. That's something what we still don't know. But there will be protected from the radiation. There will be some material which we know from Earth. It's, you know, quite friendly for them. There will be a liquid water, energy, and so on. So I would like to have a samples from Christ Planitia from some of these kilometer scale flows, which we believe that they are mud flows.
Thank you. That's very insightful. And thank you for the talk too.
Thank you. Somebody else? If not, and you will have questions later, all the time, feel free to write me the email. So that's, I'm normally replying like in 5 days, so that's fine.
Peter, we really enjoyed it. It was rare that we take our seminar series beyond planet Earth, and it was a very pleasant journey you took us on. Really fascinating.
Thank you, and I really enjoy my stay in Miami.
You're welcome anytime.
Thank you. Okay, so have a good day, and hopefully see you in the better time somewhere at the conferences.
Brilliant. Thank you, Peter.
Bye.
Bye-bye.
You. Thank you, Petr.
You're welcome.